Hello students, today we will be looking at the concept of the capacitors and the capacitance. So what is a capacitor and what is a capacitance? A capacitor is a device made of two conductors which are separated by a small distance, and it is usually defined in general terms as a device which can store the charges. That is, we can use a capacitor to store the charges, and you might have already seen such kind of devices which are used in electrical equipments. So these are the capacitors. That is, these are the generally used capacitors in case of electronic circuits. Now, usually in case of a capacitor, one conductor is charged with positive charges and one conductor is charged with negative charges. The two plates are given equal magnitude of charges, but the sign of the charges obviously will be different. That is, the two conductors will be charged with equal number of opposite charges on either of the two conductors. Now, due to this, there will be a potential difference which will exist between the two conductors, and as a result of the potential difference, there is an electric field which exists between the two conductors. So, between the two conductors, there is usually a uniform electric field which is existing. That is, if we are in requirement of a uniform electric field, we can just use this particular configuration to get it. And usually in the gap between the two conductors, in certain cases we leave the space as it is. That is, we are going to maintain either a vacuum or we'll just leave it as it is, so that the air is filling up the space between the two conductors. However, we may also choose to insert some dielectric medium in between this particular region. That is, without leaving any gap, I can fill up this region between the two conductors with a dielectric medium. So then also we can actually use the capacitor to enhance the capacitance of that particular device. So since the two conductors of a capacitor are oppositely charged and equally charged, that is, equal but oppositely charged, the net charge on a capacitor obviously is going to be equal to 0. Now, there is one more configuration which we can talk about regarding the capacitors. That is, we can think of a single conductor as a capacitor, assuming that the other conductor is at infinity. That is, we can take a charged conductor, one of the charged conductor, and we can assume that one more conductor is placed at infinity, and we can say that this particular configuration as well is a capacitor. Now, the symbol of a capacitor is just showing two parallel lines and the horizontal connecting wires on either side of these two parallel lines. This is how we actually represent a capacitor in case of a external circuit, that is. Now, the electric field which exists between the two conductors is usually proportional to the charge Q of the capacitor, and due to this, you also can say that the potential difference, that is, we already know that the electric field and the potential difference will be actually proportional to one another, and as a result, the potential difference, which is nothing but the work done per unit small positive charge in taking a small test charge from conductor 2 to conductor 1. Now we have two plates. Between this we have the potential difference. Now to define this potential difference between the two plates, we are going to define it as the work done per unit small positive charge. That is, work done per unit positive test charge we are taking, which is very small, and we are trying to move it from one plate to another plate or one conductor to another conductor, and it should be done in the direction opposite to the direction of the field which exists between the two conductors. Then we can say that the potential difference V is proportional to Q, and hence Q will be equal to C into V. Now here the constant of proportionality which we have taken C, it is called as the capacitance of a capacitor. And now usually the capacitance is dependent on the shape, size and geometrical placing of the conductors and the dielectric medium between. That is, if we are going to take the capacitor either in the form of a parallel plate, that is two plates kept parallel to one another, or we can also consider it as concentric spherical shells placed one outside the other. And we can also think about the configuration like we can have concentric cylinders with the same axis as the center. So such kind of configuration all will give us the capacitor, but the capacitance of these capacitors will be totally different. That is, they will be depending on the shape of the capacitors. They will be also be depending on the size of the capacitors as well as the geometrical structure of the capacitors. And add to it, we can also change the capacitance depending on the dielectric medium of the capacitors. That is, whatever the dielectric medium we are going to insert between the two plates of the capacitors, it will also decide the capacitance of the capacitors. Now, the unit of capacitance is given as farad, and it is usually in terms of basic units if you are actually talking about. So we talk about it in terms of farad is nothing but coulomb per volt. Now let us see how the capacitor actually works. Now since the capacitor is having two plates, here we are going to talk about a parallel plate capacitor. Usually we talk about the parallel plate capacitors to understand better. So in this case, one plate is positively charged, the other plate is negatively charged. So electric field will actually be in the direction from positive plate towards the negative plate. Now the capacitance of this capacitor can be taken as C is equal to Q by V. And we already have seen that since C equals to Q by V, for large amounts of charges Q which are stored on the capacitor plate at a relatively small value of potential difference. That is, if you have the capacitance value which is very large, if the capacitance value is very large, then in such a case we can store more number of charges at very small potential differences. So what happens if I am going to increase the potential difference then? What is going to happen? In such a case, the electric field which exists between the two plates of the capacitor will surely be very high. That is, since there is a potential difference which is very high, electric field which exists or electric field due to both the plates will be so high that they will start ionizing the surrounding air particles. That is, whatever the air particles are existing in the vicinity of these plates, they will be ionized, and they will get the ionized particles will now once again be accelerated. That is, the ions are nothing but the charges, so they surely are going to get accelerated in the presence of an electric field. And this particular these particular ions which are accelerated now move to the opposite plates, and what they do is they neutralize the plates. That is, the charges get neutralized partially, which means the capacitance or the capacity of the capacitor to store the charges is going to be limited in presence of a high potential difference existing between the two plates of the capacitor. And hence, usually what we do is we make sure that the capacitance of a capacitor is very high while we store the charges at very low potentials. So when we store the charges at very low potential, there is a possibility of storing more number of charges as compared to storing the charges at high potentials and low capacitance. So this this also actually, the high electric field also actually leads to some amount of leakage of charges. That is, since the charges are neutralized, obviously the charges are going to leak away through the external circuit. So this also is a possibility, and as a result it is not suitable enough for us to actually take the high potential difference between the two plates of the capacitor. Now coming to the next one, that is continuation of the electric field. What happens at the electric field, high electric fields? There is a certain maximum amount of electric field that a dielectric medium can withstand. That is, the electric field between the two plates of the capacitor is going to be altered due to the presence or absence of the dielectric medium. So when there is a dielectric medium, obviously the dielectric medium also will be undergoing some amount of polarization, as we already discussed in the dielectrics and polarization concept in the last video. So due to the presence of external field, the dielectric medium also is going to get affected, and there is a limit to up to which the dielectric medium can actually withstand such kind of high electric field. That is, high intensity electric fields can be actually withstood by the dielectric medium only up to a certain level, and beyond that particular level they are going to break down. So this maximum electric field above which the breakdown of the dielectric medium is going to happen, it is called as the dielectric strength. That is, the maximum electric field itself is going to be called as dielectric strength, for which the dielectric medium is not going to withstand the high electric field capacity, and obviously it is going to break down. That is, it will show random behavior where the polarization can be affected in the medium. So the polarization gets affected and certain amount of other phenomenon can be actually looked at. So this particular maximum electric field, we are going to call it as the dielectric strength. So if a capacitor has to store large amounts of charge without leakage, then obviously the capacitance should be very high. We already discussed about this. When the capacitance is high, the potential difference and hence the electric field do not exceed the breakdown limits. That is, it's an obvious thing that when the capacitance is high, we don't require very high potential difference in order to store the charges. So what we do is, when we will maintain the capacitance high, and the potential difference is usually maintained at a very low level, in such cases as well we can store more number of charges in the capacitor. So there is a limit, which means knowing all these points, we can say that there is a limit to the amount of charges that can be stored on a capacitor without considerable leakage. That is, the limit up to which the charges can be stored in a capacitance, it is actually going to be a finite value. We cannot actually store infinite number of charges on a capacitor. So what is the extent or up to which the charges can be stored? It is decided by the two factors, that is, one is the capacitance, the other one is the potential difference. In case of high potential difference, there is leakage of the charges, so we usually avoid the case where the potential difference is actually going to be very high. Instead, we will actually keep the capacitance of the capacitor itself as very high, keeping the potential at low. Also, we can say that since the charges are proportional to the capacitance, as we already have seen in this case, we have already seen over here. Yes. So we have seen over here that the potential difference is proportional to the potential difference. Potential difference is proportional to the number of charges stored on the capacitor plates. But from this equation, let me just show it to you. See here, C is equal to Q by V, which means if I am going to keep the potential difference fixed, that is, the potential difference between the two plates of the capacitor, if it is fixed, then I can see that C is proportional to Q. That is, as the C is going to increase, Q also is going to increase. That is, Q is proportional to C. More the capacitance, more the number of charges that I can store. So the same thing cannot be told about the potential difference. Of course, when we increase the potential difference, also we can go on, we can store more and more number of charges. But there are leakage effects. That is, the leakage of the charges due to high electric field, which comes as a consequence of high potential difference, cannot be avoided in such a case. So to overcome this particular limitation, we usually keep the potential difference at very low and a fixed value, and we take the capacitor with a high capacitance to store more number of charges. So this is about the capacitance of a capacitor and what are the limitations of the capacitor. Now we will deal with the working of the parallel plate capacitor, and of course certain amount of derivations are there related to the parallel plate capacitor. Now for this we have taken two plates, plate 1 and plate 2, and plate 1 is charged with the positive charges and plate 2 is charged with negative charges. So obviously the plate 1 is going to have a surface charge density plus sigma, and plate 2 is going to have a surface charge density of minus sigma, and between the two plates there is a distance of separation of d, and the electric field is from plate 1 to plate 2. So we are not going to use any kind of dielectric medium in this case. we will take a generalized case initially where there is only vacuum filled between the two plates. Now we already know that the surface charge density is given by Q by A, that is charge per unit area. Now from this we are going to make sure that we are going to get a relation for the capacitance of a capacitor. To get this, firstly we have to find out what is the electric field outside in the outside regions of plate 1 and plate 2 and between the two plates, that is in the region 3. We'll mark it as region 1 outside, region 2 outside, and region 3 is going to be on the inside. So electric field outside the plate 1, that is in the region 1, we can see that E1 is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught equals to 0. Now why is this? The reason is very simple, because there are no charges residing on the outer side of the plate, right? So since this is not connected to any kind of battery or the EMF source, so what happens is the charges are going to be residing only on the inner side of the capacitor, that is inner side of the two plates. So due to this, there is no electric field which exists on the outer side of this plate. Similarly, we also have the electric field being equal to 0 on the region outside the outside this plate 2. But however, we can see that the electric field which is existing within this particular region is going to be E is equal to sigma by 2 epsilon naught plus E equals plus sigma by 2 epsilon naught. Sigma by 2 epsilon naught for the positively charged plate, and for the negatively charged plate, since the direction of electric field is going to be opposite in direction, so we are going to take it as minus of minus sigma by 2 epsilon naught, which becomes plus sigma by 2 epsilon naught. So when we add, we can see that it is sigma by epsilon naught equals to Q by A epsilon naught. So the total electric field which is existing between the two plates is E is equal to Q by A epsilon naught. Now this particular field is always going to be from the in the direction from plate 1 to plate 2, that is from positively charged plate to negatively charged plate. And this particular field, we are going to assume that it is going to be a localized field and it is uniform everywhere within the region. Okay, so we'll also come to the edge effects in the later part of this particular session. Now when we talk about this, since this is a finite, we have actually considered, we have not considered the size of these two plates. Initially we have considered that these two plates are going to be infinitely larger plates, and hence we took the electric field as E equals to sigma by 2 epsilon naught. But in case if the two plates are finite, so usually in real cases we usually take the dimensions of these two plates as finite dimension, that is the area of them is known. So in such a case, there are the electric field lines usually bend outward at the edges, that is usually they will not be linear, instead they will be bending outwards, because the charges will accumulate more at the edges, and hence there is the charge distribution is not considered to be uniform. But however, we find that the area of these two plates, that is the area of the plate, if you are going to take it as A, it is found that the area is going to be very much greater as compared to the square of the distance between the two plates, and as a result this particular edge effect, which we call it as the fringing effect, is usually ignored. So on ignoring this, we can safely assume that the electric field in the regions between the two plates is uniform, and in such a case the potential difference between the two plates can be given as E into D, that is electric field multiplied by the distance of separation, and this will give us V is equal to 1 by epsilon naught into Q into D by A. Okay, so due to this, now we already know that the capacitance of a capacitor is C is equal to Q by V. So this will be equals to epsilon naught into A by D. So this is the general equation which gives us the capacitance of a parallel plate capacitor. Now this is about the expression for the case where the capacitor is filled with vacuum or air. Now what if we are going to fill the gap between the two plates with a dielectric medium. In such a case, there is polarization. So due to the polarization effect, obviously the electric field is going to be altered, and the electric field inside between the two plates of the capacitor is now given as E is equal to sigma minus sigma p by epsilon naught. Why this sigma minus sigma p? The reason is very simple. Sigma is actually the charge density which exists without the existence of a dielectric medium, and sigma p is the polarization. Due to polarization, whatever the charge density is created inside the dielectric medium, we are going to take it as sigma p. We already know that this particular charge distribution is going to give us a reduced charge density, and so we get the electric field to be given as sigma minus sigma b by epsilon naught. So the obviously once again when we put the equation of potential difference, we can see that V is equal to Ed equals to sigma minus sigma p by epsilon naught into d. Now from this we can say that the sigma minus sigma p, in this case the potential the dielectric distribution of the charges or the charge density which we have over here, it is directly proportional to the electric field. We already know that more the number of charges, more number of charges per unit area of the surface, more will be the charge density, more is the charge density, more is the electric field, right? So due to this, we can also safely say that sigma minus sigma p is proportional to sigma, because the sigma p value is going to be fixed for the uniform electric external field. So due to this, we can say that sigma minus sigma p is going to be proportional to sigma. From this, we can safely say that sigma minus sigma p is equal to sigma by k. Here we have taken 1 by k as the proportionality constant, or k is a constant. Now this k, which is a constant characteristic of the dielectric, that is k is actually a constant which is representing the properties of a dielectric medium. Okay, and it is evident that sigma has to be always going sigma is always going to be k greater than 1, that is k will always be greater than 1, that is the dielectric constant which you have taken k, it is greater than 1. And for the air medium, that is if we are going to take air medium, k will be equal to 1. Okay, so from this we can see that now the equation actually changes. Equation for the potential difference between the two plates of the capacitor is going to change. The potential difference is going to be given as sigma into d divided by epsilon naught into k, or it can also be given as qd divided by a epsilon naught k. And obviously the capacitance expression also is going to change. So capacitance is going to be equal to q by v equals to epsilon naught k into a divided by d. So note the difference, that the capacitance of a capacitor without the dielectric medium was epsilon naught a by d, whereas the capacitance of a capacitor with the dielectric medium is C is equal to epsilon naught k into a divided by d. That is, if the dielectric medium of higher dielectric constant is taken, then we can have more capacitance. More capacitance means the more number of charges can be stored on that capacitor. Now from this we also have a relation between epsilon naught and epsilon. We can see that epsilon naught into k becomes equal to epsilon, which is called as the permittivity of the medium. Okay, so we have already discussed about this, that is at k equals to 1, epsilon becomes equal to epsilon naught, which is nothing but the permittivity of the free space or the vacuum. Okay, and the dielectric constant can also be given as ratio of absolute permittivity or the permittivity of the medium by permittivity of free space, and it can also give us the relation between the capacitance of the capacitor with the dielectric medium and without dielectric medium. That is, capacitor dielectric constant can be given as C divided by C naught, where C is the capacitance of the capacitor without with dielectric medium, and C naught is the capacitance of the capacitor without the dielectric medium. So obviously the greater the dielectric constant of the substance, greater will be the capacitance of the capacitor. Now remember one thing, capacitance of the capacitor also can be actually varied by changing the area, we can see that capacitance is directly proportional to area, which means if I am going to increase the area of the plates, then also the capacitance is going to increase. And at the same time, if I am going to decrease the distance, that is, if I am going to decrease the distance between the two plates, then also the capacitance of the capacitor is going to increase. More the capacitance of the capacitor, more will be the charges stored in it. So this is about how the capacitance, the capacitor of the capacitor actually works. And more is going to come in the next video. That is, I'm going to discuss about the working principle of the capacitors when there is a battery which is connected to the capacitor, and we are also going to look at the combination of the capacitors and how the energy, electrical energy, can be stored in the capacitor in the next video. Thank you for watching this video.